Alright, welcome back. Now we will discuss batch normalization. It's not specifically linked to recurrent neural nets. It applies to all neural nets, COV nets, dense network. And in order to show you what we will do, I want to go back to video number 31 where we discussed feature scaling, feature normalization. So the problem is as follows. You have x1, x2, two features, and the range of x1 is from 0 to 5 and is smaller than the range of x2, which is between 0 and 20,000. So that means that when you're going to have contour plots, it's all going to be a very small set here that goes very far compared to the variance in the x1. So this variance much bigger than this variance. And of course, you can feel that it will not really work well with gradient descent. In gradient descent, for this to work well, we need nice, preferably circles as our contour plots, and then we can just converge to the minimum. Here is very difficult to do. Alright? So in order to solve this problem, we basically did a transformation. So you have here your data with mean mu and standard deviation sigma. So this is my x. I transformed to z, and in z my mean was 0 and my standard deviation is 1. So this transformation solves this problem, and so my z equals my x minus mu divided by sigma squared. And this is how we got from x to z. Alright, now in deep learning we have several layers. So that means that each layer is an input to the other layer. And the question is, shall we apply normalization here as well? The answer is yes. So here you have your layer, AI. This could be, for example, A2. And this could be Z2. So what we're going to do is we're going to apply normalization on Z2 before Z2 is activated by A2. And here again, our Z2 normalized will be Z2 minus the mean and divided by sigma squared. And we're going to add an epsilon here, and this epsilon is purely to avoid division by 0 or division by a very small number. So we can apply normalization in each of the layers before we activate. Now, you will see that there is two parameters defined, gamma and beta, because we don't necessarily want to have mu equal to 0 and sigma equal to 1 in all cases. We want to have some degree of freedom, and basically what we want to do is let the network learn these parameters. So here we're going to define a Zi normalized Zi tilde, and that equals gamma Zi norm plus beta. So this gives us some flexibility with respect to these numbers. It's a bit weird, it's a bit counterintuitive, because basically what you did is you took your data and you put it around 0 and 1, whereas this here, works again the other direction. Now you can choose gamma and beta in such a way that Zi norm is Zi tilde norm. That's not an issue. So why is batch normalization useful? Well, I draw a neural net here with 5 layers. And layer 4 and 5, if we use mini-batch stochastic gradient descent, which is, in most cases the case, layers 4 and 5 will see different distributions, with mu and sigma, because you take a little batch and the distributions of all these batches will not be the same, which is not very good because it will create some noise and it will slow down your gradient descent. Now what you can do is make sure that the distributions coming in are all nice Gaussians. These are then Gaussians with mean 0 and standard deviation of 1. So it will reduce the variation seen by these 2 layers. It's not a question to use batch normalization or not. Batch normalization is the de facto standard. And we will use it in most cases. All right.